Okay, the afternoon session starts with Felix Kubler from Zurich and SFI talking about uncertainty quantification in general and then with application in climate economics. So the floor is yours. Thanks, Felix.
Thanks. Yeah, so this I wrote based on joint work with Alex, Simon, and Takafumi. I wrote that because I'm going to say a bunch of stuff today that's going to piss them off. So that's why it's based on joint work. It's not actually representing the joint work because they would be pissed off at me and I want to keep them as friends. So I call it based, and Takafumi, who's not here, who did actually most of the work. No, Alex did most of the work, of course. Let's talk a little bit about what engineers call uncertainty quantification. So the plan is to give you an introduction, just theoretically, explain what we want and why we want it, maybe. And then I spend some time on how to compute stuff. I'm going to talk about Gaussian process, something which Simon has not mentioned, but is actually a large part of Simon's work. So Simon pioneered Gaussian processes in economics. He's too modest to point it out. So I'm going to point it out for him and going to teach you a little bit about GPs. And then I'm going to do a climate economics application, which is going to be just in time for you. So now you're still a little bit full of energy from lunch, but when I start with the climate macro application, everybody's going to be close to being asleep. And then we're going to have some fun because it's just blah, blah, okay? Okay, so what's uncertainty quantification? So it's some stuff engineers and scientists do. So they call it studying the impact of aleatory or epistemic uncertainty on computation models used in science and engineering. There's guy Sudre, he's in Zurich at the Technical University at ETH, and he has a huge share with millions of postdocs and millions of assistants who do this for him. And in engineering, it's a big thing. So if you go to interdisciplinary conferences and you say you compute Sobol indices, they right away love you more. So they, you get commerce and economists, so you think you're a complete piece of shit. And then you tell them about Sobol indexes, and they come and hug you and say, "Oh, you're the first smart economist I met." So, I'm going to tell you what it is, so you can also impress engineers. But the question is, does it make sense in economics? And to be honest, I'm not so sure. Okay, so we can talk about it. Maybe we end up thinking it's a complete waste of time in economics. So Daniel Hardenberg, who is an economist, did a postdoc in ETH and teamed up with people from Sudre's share to write this paper on using UQ in economics. It's published in QE now, the paper. And I remember he came to present it in Zurich. And I was so pissed off. I thought it was such bullshit that I was really super nasty the entire talk. And now the entire engineering department in ETH thinks that I'm the nastiest, most arrogant asshole in the city of Zurich. So I just didn't understand, okay? I just didn't get it, why it's useful. Now I think I have some lever to claim it's useful, but you can tell me it's all fucking bullshit and I'll take it nicely, okay? I'm a positive kind of guy, so we don't give you grades, so what can I do? I'm gonna say, yeah, thank you. Now, maybe it makes a little bit more sense. So to my defense, Hardenberg did it in the stochastic growth model. And there I still think makes no sense. In macro climate modeling, it might make a little bit more sense because a lot of the uncertainty there is scientific uncertainty, like uncertainty about the climate, which you can go talk to climate physicists about and understand what they see, and then maybe it makes more sense. Okay, so in the very least, I'm going to try to, at the end of the presentation, I try to convince you that it certainly makes sense in climate macro to do a little bit of uncertainty quantification. Okay, so here's what we're going to do. So we have some model. Later on, it's going to be simply a model of the world climate and a planner who's trying to figure out how much money to spend for mitigation today to make climate change less bad in the future. And so he solves some problem, and the question is, how much money should he spend today? And this is the outcome of some model. So it's going to be a dynamic programming model. But of course, there's a lot of uncertainty about the model. So there's some fundamental uncertainty how to write down the model, but much of the uncertainty we can reduce to uncertainty about parameters, okay, to uncertainty about real numbers. So we think of this M as a function of theta, and I should say it's a function, of course. So in economic applications, there might be problems of multiple equilibria, and it's not even a function. So many of our models, we cannot rule out multiplicity, and if we have multiplicity, of course, none of what I'm going to say today is going to apply. So we're going to assume it's a function, and actually we're going to assume it's a smooth function, and all the regularity assumptions you want to make, I'd be happy to make them for you, okay? And so these theta is the input, and the outputs are called quantity of interest in this literature, okay? So this is how much money should we spend for mitigation, the Y, okay? And so what uncertainty quantification does, it says, okay, so we put a distribution over these parameters. So we think for some reason we know some distribution over these parameters. And then what's going to be the distribution of Y? How can we characterize it? Okay. So when is it relevant? Well, so further I should say, to be honest, we have to assume the CDF is independent across parameters. So that's already a strong assumption. And you can relax it a little bit, but not really very much. So we're going to assume that we have this distribution of parameters, which is they're independently distributed according to some distribution function. Where do you get the distribution function from? Well, in my climate application, I will argue that that's what people believe, perhaps, or that's the distribution you can measure what scientists have over these parameters. Maybe it's just some distribution which comes out of some measurement, some estimation, and these are standard errors. So that's the setup. Okay. So the question now is, how do we characterize the distribution over Y? And we're going to be interested mostly in the variance. Okay, so we're going to take like this old-fashioned finance point of view that we mainly, so distribution, we're mainly interested in the variance. There might be many other moments which are problematic and we care about, but let's start with a very simple mean variance framework. And so we want to know the variance of this distribution of the quantity of interest, given distributions of the parameters. What's the variance of the distribution of the quantity of interest, okay? And if this variance is large, obviously we're in trouble, okay? So that's a typical complaint people have about economic models, which is that, you pick some parameters and you get some answer. If you picked other as reasonable parameters, the answer will change completely. So this, one can sort of formalize a little bit by saying, well, this variance better be small, or we need to invest more time trying to get better data to pin down our parameters better. Or we need to change the model and put the parameters into the model differently. Because if this variance is large, we're screwed. And in particular, we want to figure out, and that's now the whole point of this uncertainty quantification, which parameters drive the variance. Okay, it could be that you have like 10 parameters in your model, the variance is huge of the outputs, but it comes really only from one parameter, from one number which you don't know, and all the other numbers play not such a big role. Okay, so how can we formalize this? So we want to find a way to formalize the question, which input parameter contributes the most to the variance of the model, okay? And so we're going to see that Sobol, some Russian dude, came up with some idea how to do this, and these are called Sobol indices, which turns out, I think it's fair to say, to not exactly do that job. So they're useful for many reasons, but they're not exactly the best way of doing this. Turns out the best way of doing it is to report the Shapley value. Okay, so I don't know how many of you have heard about the Shapley value. I'm sure they still teach it at Caltech. So if you're a PhD student in Caltech, you know about the Shapley value. They taught it when I was at Yale, but that was a long time ago. Nowadays, nobody at Yale knows what the Shapley value is. So I'm going to tell you a little bit about the Shapley value. It's one of these very rare occurrences where, usually economists read some computer science books or, and then they copy from computer scientists. Whatever computer scientists do, we blindly follow. Here it went the other way around. So some computer scientists read Shapley and thought, oh, that's a good way to express this idea what parameter contributes most to the variance. And so now machine learning Shapley value is actually very commonly used for all sorts of things. But it's an economic concept from economics. Okay, and so if there are some parameters which have very large Shapley value, or contribute very much to the variance, this means we have to do something about it. As I said, either get some data or change the model. And I'll give you an example how we change the model in what we think is a reasonable way. Okay? So that's the plan. Okay, so to understand these Sobol indices, we want to, maybe some of you have seen it, or if not, I'm going to explain, recall what the ANOVA functional ANOVA decomposition of a functions. Okay, so if you have a multivariate function which maps from Rp, so p-dimensional space, to R, you can obviously write it as some constant function, and then p functions that just depend on one variable, p unit variable functions, f1 of x1, f2 of x2, and then a bunch of functions that just depend on two variables, f of x1, x2, x1, x3, and so on. And then a bunch of functions that just depend on three variables. And then a bunch of functions, and at the end, as a function that depends on all the variables. Okay, so this is just a fancy notation of saying that, okay, so we can write our true high-dimensional function as this sum of all these smaller dimensional functions. Okay, and of course, there are many ways of doing it. You could just take the last f of the entire set to be f hat, and you're done, and all the other functions are zero. Okay, so that itself is not a very interesting thing. So you want to find a systematic way of doing it so that these functions pick up a lot of the variation. Okay, so it's a way of saying, okay, we want to find a ways to say, obviously, so for function approximation, for many other things, it's much easier to approximate p one-dimensional functions than to approximate one p-dimensional functions, okay, because of the curse of dimensionality. And so if the ANOVA decomposition would be good until this, many of the problems would go away. We wouldn't need neural nets for any of this stuff. We would just do, one-dimensional function approximation. But of course, it doesn't. So you need higher order terms, but you want to put in the higher order terms in some systematic way so that they add less and less. Okay, so that the first terms carry most of the weight. All right. Okay, and so this is done by defining recursively f hat of every s, so s is a subset, so you have p-dimensional domain, and so for every subset of this domain, you have your f hat s, and you define f hat s as the integral over x minus s, is taking the variables in s out of f hat with respect to dx minus s, minus your previous approximations. Okay, so you start with the constant term, so the constant term is just the integral. Okay, so the constant term is just the average, as you would think. So approximate a function. What do you pick as a good constant term? Well, the average of the function. Then the next terms are sum of iterations. So you start with the average of the function, that is f0, and then recursively define f1 of x1, f2 of x2, and so on up to your entire function. Okay, so you can decompose the function under, has to be square integral, but all these, all these anal math things we're not going to mention here this afternoon. Okay, so square integral, all these things, don't tell me this, it holds always. Okay, so okay, so this is a unique way to decompose these functions, and so here's just to do it for yourself. So as I said, you start with the intercept. That's just the average of the function over x. And then what are the univariate terms? So fi of xi is just the integral taking element I out of x, f hat of x minus f hat of 0 integrated with respect to x minus s at any point xi. Okay, so this is, this should be x, but the only thing that varies here is xi. Okay, and so these are the univariate terms, and you do it for each pair, and so on and so on and so forth. Okay, and so that's how you can decompose any multivariate function into these terms. Okay, that's what we call functional ANOVA decomposition. And it's easy to check that with these definitions, you have these orthogonality conditions. So you have clearly that for any non-constant term, they all have to integrate up to 0 because all the average is already in the constant term. So all the other terms integrate up to 0. And you have this orthogonality condition. So if you take any S and B, then f hat S, f hat B are orthogonal. And it turns out that if, another way to derive this decomposition is to start with these requirements, and then turns out that the functional ANOVA decomposition is a unique decomposition that gives you this. Okay? So that's a common way to sort of try to pick up the variation of a function in these low order terms, in these univariate terms. Okay, and so we can now think of the variance, right? So we can just say, we decompose the variance of the function in exactly the same way. Okay, and that's what's called the Sobol decomposition. Okay, and so the Sobol indices are nothing else but renormalized variances of these ANOVA decomposition terms. Okay, so in particular, the first order Sobol indices are just the variance of the f hat I terms, which we construct like this. Okay, so just first order Sobol indices for each parameter, the variance of the term of the first order term of the univariate term that comes out of the ANOVA decomposition. Okay, go ahead.
You say, let's take x to be a random variable.
Yeah.
Is x the input of the function?
Yeah. Yeah. So x is supposed to be the input of the function or the parameters in our set.
So you're integrating out dimensions of x essentially.
Mm-hmm. Exactly. So if you look at maybe it becomes clear just if you look at the definition of the first order Sobol index, so you can write that as the variance of the expectations. So for parameter I, it's the variance over I of the expectation of the function integrating over everything except for I. Okay, and then normalize. So the denominator is just a normalization. You want them to add up to less than 1, but the crucial one is the numerator there, which says the first order Sobol index of a parameter I is the variance that I contributes, but not what does it mean, the variance that I contributes? The variance that I contributes to the conditional expectations of the output given each theta I. And the higher order Sobol indices are defined in the same way, simply by always taking these recursive definitions of the functions and then taking the variance. Okay, now of course you can see that it grows with some factorials. It's a combinatorial problem. So second order Sobol indices, you already have 2 choose P. Third order Sobol indices, it gets there are a whole bunch of them. Okay, but the first order Sobol index, there are as many as variables, so that's to first approximation a good thing to figure out if you want to do this global sensitivity analysis. Okay, so you want to figure out first you want to figure out the overall variance of your output, and then you want to figure out what contributes to the variance in the first order. So what are the individual Sobol indices for every variable? Okay. Now it's not exactly what we want, because clearly the first order effects might hide a lot of variance, right? So a lot of variance, some variable could contribute hugely to the variance of the output, not by itself, but by some interaction it has with some other variable. Okay, so clearly these first order Sobol indices cannot be the whole story. And that's why they're second order and third order. But as I said, second order and third order become very hard to report, because if you have you have 10 parameters, you have hundreds of numbers to put in a table and nobody's going to look at them. And so that's not a good way to do it. Okay, so a better way to do it is to put the Shapley value. Okay, so there was Shapley when he got the Nobel Prize. He got the Nobel Prize not for the Shapley value, but for Gay Shapley. Yeah.
Excuse me, can you just where does the orthogonality condition get in? Like, I didn't see how that.
No, it didn't. So the way I developed this, I just said you can show that by the definition. So this follows from the definition. If you take these recursively defined things and multiply them out and integrate, you see that it has to integrate up to 0. So it follows from it. It's a much harder proof, which I certainly can't do now, and probably could never do even in my best times, to prove that given these conditions on orthogonality and on average, the unique decomposition is ANOVA that but it's sort of not super relevant. What's relevant is that you get these orthogonality conditions, and that's why you can decompose the variance of it. Yeah.
Probably as why are we investing in all of this machinery instead of something like PCA or projection method, where we can kind of just back out the variance directly?
What do you mean by backing out the variance directly? I understand.
In the sense that you have certain, you have certain variables, right? And you can look at kind of varying over the range of those variables, how much the outcome changes, and I can just kind of see reduced. Oh, okay, this axis contributes most of the variation.
Right, but that I am not exactly sure you remember the way you described it. That sounds like the first order Sobol index. So if you do this, how do you fix the other variables? Okay, suppose you have 10 variables. You take variable 1, compute the variance. At what values do you hold the other variables fixed? Right, the variance is not defined unless you take a stand on the other 9 values. And here the stand is you just integrate out the other 9 values. Okay, so but this is precisely the first order Sobol index, which you mentioned. Now, I want to say that it's not exactly what we want, because we want a little bit more, because there might be interaction terms, right? So we want to capture the effect that the first variable together with the 7th variable really kills us in some sense. And that's not if you just take the variance in one direction.
On your slide, functional ANOVA, 2004, that we were showing.
Yeah.
On the first line, you are defining, yes, exactly. The first line, you are defining f hat in terms of f hat s, and in the line afterwards, you are recursively defining f hat s in terms of f hat, among other stuff.
Okay. No, this is not the definition of f. No, so sorry, I was very unclear there. Good thing you called me. No, that's not the definition of f. F hat is some function, and this is not the definition. This is just the question. We want to write this function f hat as the sum of these other functions. The definition of f hat, so the definition of f hat is going to be the solution to a dynamic programming problem. The definition of f hat can be anything. It can be any arbitrary, complicated mapping from parameters to numbers. So f hat is any square integral function, and then we want to decompose it like this. So this is not the definition of f hat. This is just a way to write f hat. And each of these terms is defined using f hat. Okay, no, I when I made the slide, I understood that the notation is bad and people are not going to like it, but then I was too lazy to change it. So I don't know where the head is on the F, okay? To be completely honest, you can take the head off the F, then it doesn't look like this, but these F hat S are different functions. So whenever there's a subscript here, it's a different function than the whole F hat function.
I see, so it means that if I take that sum on the bottom line, I will recover F hat.
Exactly,
Okay.
Exactly, by definition, because you go up all the way to the entire set, and if you have the entire set, you pick up the rest of the variation.
Okay, understood.
Yeah.
So I think I understand everything for the f hat part, but just the thing about where you said the first order Sobol indices are SI equals the variance expectation thing. What is, like, because S on all the previous slides is basically just like a subset of the variable.
Yeah.
It's
Yeah.
subset.
So these are the singleton sets.
It's what?
The singleton sets. The subsets that are just singleton. 1, 2, 3. So the subsets here are where is it? I have a nice place. Where is it? Sorry. Here. So the Sobol indices are just the variance of these guys, the first order. And the subset is a singleton set, which consists only of 1 point.
So is SI then the variance of, like, so
Yeah, SI is the variance of this guy.
So, okay, so S1 would be the variance of F1.
Exactly.
S1?
Yeah.
Oh,
Exactly. And the second order Sobol indices are the variance of these guys.
so is SI, would S1 be the same thing as sigma squared sub 1 F hat 1?
So it's sigma squared sub 1 f hat.
Because essentially.
Yeah, exactly. Yeah.
Now let's take X to be a random variable and get.
Yeah, that's what the slide was supposed to mean.
Okay.
Okay, now we talk about so, but I wanted to convince you that we don't do so, we do Shapley value. Although, as I said, so if you talk to engineers, you gain a tiny bit of credibility from the super low life economists to the slightly not so low life economists if you know the so-called indices. But then you come with Shapley, and he was an economist, so he won the Nobel Prize for Gale Shapley, which is also something which, you know, computer scientists picked up from us. Well, from us is a bit of an overstatement. It's all from Shapley. There's one guy who had some influence. And he was a bit of a crazy guy, apparently. But okay, so nobody teaches that anymore, which is sad, because it's one of the things in economics which has absolutely no applications and is completely useless, but nice math, which is cooperative game theory. Okay, so so a cooperative game is a bunch of players, and it's defined by what's called a characteristic function, which tells you in some sense how much each subset of players can achieve when they go together. Okay, so there's a single guy, he can has some characteristic of the single set, the characteristic function of the entire set to be normalized to 1, and then you want the characteristic function to be defined on all subsets of n. So that's the definition of a cooperative game. And so Shapley asked, what's the value of each game? Can we find, so across all games, can we find a concept of a value which gives you the value of the game for a given player? Okay, and so of course we can do that, but it's supposed to have certain axioms. And so Shapley proposed these 3 axioms, which the symmetry and carrier axiom are completely obvious. I think I don't have time to explain this. If I turn this into a class in old-fashioned microeconomic theory, I think a lot of people are going to be very pissed off at me. So I'm going to cut short on the Shapley index, but here's this bunch of axioms. Carrier axiom is just that the null player, somebody who never adds any to the characteristic function, has value 0, and that what you call efficiency, that if you put all players together, they have the largest value. And then he has this slightly obscure additivity axiom, which I'm going to mention again later on. And he showed that with these axioms, the unique function that satisfies all these axioms is what's now called Shapley value. He himself, I think, didn't call it that. I'm not so sure. So all these old guys found some other names that are not so vain like people today who name concepts after themselves, like the Scheidegger neural net. And but
Did I?
I'm kidding. I was just trying to see if you're paying attention. But of course, there was a mistake to say Scheidegger. Then he woke up. Anyway, so the definition of the Shapley value is a slightly obscure thing because it involves this factorials. It's some combinatorial thing, but it assigns a unique value to each player of the game. So it's a Shapley value for player I for game B, and it assigns this unique value. And so the idea is to take this instead of first order Sobol indices, second order Sobol indices, and so on, to take this to sort of express how much does each variable contribute to the overall variance. Okay, so while in cooperative games, obviously you thought of people cooperating and doing something good. In this application, there are all these parameters that cooperate and do something bad. They introduce variance into your economic model, variance you don't want. So you want to make this small, but it's the same concept. So whether it's something good or something bad, some output. And the best way to summarize how much each parameter adds is just to compute its Shapley value. Okay, this expression. And so it turns out, so Owen, a statistician, has this couple of papers in 2014 and following that tell you about the Shapley value. Oh, I forgot to say, I'm such an idiot. I forgot to say on the first slide, I was so distracted by, so the paper which this is based on is actually in the GitHub repository, but it's hidden under slides, okay? So I didn't want to put it as a paper so that people who are not here don't find it right away, but the paper is hidden under slides in the GitHub. And so in the paper, we give all the references and all the things I talk about here. You can all read that in the paper, okay? So anyway, so Owen suggested to just take this Shapley value of each input parameter, okay? But so let's think a little bit about, do the axioms make sense? And it's clear for the carrier axiom, and it's clear for symmetry, but it's not so clear for additivity. I didn't tell you what it is, but if you know, then you sort of wonder, additivity doesn't make any sense here. But Owen noticed that later, after Shapley, a bunch of theorists, so in particular Peyton Young, found out better ways to, so they replaced additivity by something else. And so Young replaced additivity by the marginality axiom, which says that if you take the value of player I for coalition S as a difference of the value S gets with I, so for coalition S is not a member, the difference of the value S gets with I to what S gets without I, then the mathematical principle says, if you compare two games, V and W, if Vi equal to Wi, then the Shapley value for Mr. I for V should be the same as for W. Okay? So now if you think about it, this is precisely the axiom we want for uncertainty quantification. So I want to argue that in uncertainty quantification, this is precisely the axiom we want to impose on what's a good measure of how much to the overall variance does each variable contribute. Okay, because this marginality axiom is something we really care about in our uncertainty quantification. Okay, so whether yes,
Vi equals to Wi for all the S.
For all S, yes, for all S, yes, yeah. Okay, so whether we like it or not, what people propose and what we are following is to compute this thing instead of the Sobol index, compute this value for each input parameter I to express how much it contributes to the overall variance of outputs. Okay, and now you see that this is, so if n is large, this can be problematic, right? So if you have 20 input parameters, you have 20 factorial here, and you have the sums. So you have to find a way to sort of approximate it numerically. And Owen did that. So this Owen paper, which I cited earlier, found some approximations for the Shapley. But that's what we want to report. Okay. Okay. So that was very briefly the theory of uncertainty quantification, because there are more concepts in uncertainty quantification which people report, like univariate effects and so on. But the key idea is this thing that, you know, there are these parameters which you don't know very much about. They are, you know, if you put a distribution over them, you want to know what's the variance of the output, and you want to figure out which input parameter contributes most to the variance. And we do this by the Shapley value.
Yeah, so when you say that a parameter is out of the coalition, so to speak, is that putting it equal to just the mean of the distribution? Like the parameter will always can be included in the model, right? So what does it mean to take it out of the?
No. So this is so this would be part of the ANOVA decomposition. So this would be the variance contributed of the terms of the ANOVA decomposition, which include S plus I. So suppose S is 1, 2, 3, and I is 4. So you would need to compute. So that's why it's very hard to compute. You would need to compute the variance of the ANOVA decomposition of the parameters 1, 2, 3, and of parameters 1, 2, 3, 4, and take the difference. And that would be this VIS.
Yeah, but the fourth parameter will always be in the model, right? Then you just put it to the mean of the distribution, or like there must be some idea, like you can just not remove a parameter from the model. Right?
Oh, so you're saying what happens if it has very high variance?
No, I say you start with the 3 parameters.
Yeah.
Then you add the 4, right?
Yeah.
When you calculate the variance of the first 3,
Yeah.
there must be some sort of assumption what happens with the 4, right?
Yes. So it's not the variance of the first 3; it's the variance of the term in the ANOVA decomposition. Okay, let me show you the. So it's this decomposition we're looking at, and so this decomposition has a term f hat 1, 2, 3, and this f hat 1, 2, 3 term has a variance where you keep the others completely out, but it's a variance. It only depends on 1, 2, 3, and so you can compute its variance. You don't have to take a stand what the other variables are, because you've decomposed it in a way that it only depends on 1, 2, 3.
when you compute variance, if I look at the way the integrals were defined earlier, it's as if all the x's have the same likelihood. Is that correct?
No.
So that this would give some
so
region for your states?
good question. No, so let me give you two answers. So this is just the functional anomaly decomposition is here just derived away from stochastics. So these integrals are just the back integrals of the functions. They're just saying we can decompose the functions. If we compute the variance, of course, we have to integrate with respect to PDF, which in the theory you can pick. So you take a stand on what is a sensible prior distribution, what do you think, how is the distribution of parameters, and you use it in integration.
So now in this integral, you're adding the likelihood of each
exactly.
combination of x's. Yeah.
Well, no, so this is just a decomposition to get the f hat, but if you, I skipped over it, if you take this is the integral. I didn't write it out, but this, of course, is the integral of each term. And so it would be the integral of each term with respect to the distribution function, or the PDF, which you have to pull out of your butt. But yeah, which, or and as I said, so we want to assume that it's independent, which is a pretty strong restriction, but I don't know how to do without that. Okay, so now it becomes a little lighter. Don't despair. There's hope in the near future because we are done with the definitions. So now comes some computation. So how do we computing this stuff? Okay, and so we have to compute these integrals over parameters of a model. So that seems like a hopeless thing to do, especially if we have a large number of parameters. Okay, so that's why the title of the paper has deep in it, because if you use deep neural nets, you can just add the parameters as state variables. Right, so if you have as your state variables the wealth of me and the wealth of Simon and the wealth of Alex, you could say, so that's your state variable in some savings problem. But we also add the risk aversion of Simon and the risk aversion of Alex and the risk aversion of me. And the mechanics Simon explained for his deep neural nets doesn't care whether these variables change over time. It just solves it for different values. It simulates, so you would have to obviously, so the simulation step becomes a little bit different because you have to draw these from randomly from a set, but you can just draw them in the simulation and you can compute the solution of the model, not only for one value of parameters, but for a whole range of value of parameters, okay? So the fact that deep neural nets work so well on very high dimensional problems means if you add the parameters as state variables, you add like 5 state variables to your problem, which already had 60 or 70 state variables. It doesn't make such a big difference because now you have 75 state variables. Okay? And you can just solve it. And then you've solved it for all the values. Now, that's actually not what I'm going to dwell on here. I want to take a slightly different stand, and now I'm afraid that Simon is going to kill me, which is to say, these neural nets are a little bit tricky. Okay, there's problems verification, and there might be some problems which you don't like so much. So in this literature, in this UQ literature, typically people build what they call a surrogate model, not with neural nets, but historically with polynomial chaos expansion, or more recently, much more efficiently with Gaussian processes. Okay, so you have a way, maybe neural nets or something else, to find solutions to your model for each parameter value at relatively low cost, but not at cost 0. Okay, so this deep idea, cost is almost 0. You just compute it for all the parameter values and then you evaluate it. But maybe you want a little bit more than just the value of the policy function. Maybe you need the simulation step because you want some moment or something of your model. And so it comes at some cost to compute your model for a given parameter. But in order to integrate, so, doesn't matter how you want to integrate. You can do Monte Carlo, you can do monomial roots, you can do Gaussian quadrature. But if you integrate, you need to know the value at many parameter points. Okay, if you want to find a good approximation of the integral. So instead of computing it at every point, the idea which people do a lot, certainly in this UQ literature, but also in many other fields, is to build a surrogate model, which is to say, essentially, you just do a very good, find a very good way to do function approximation and approximate the points you've solved and hope that all the other points are well approximated by your function. Okay, and so the question is what function to use. And there comes in a little bit of magic, which is that Gaussian processes do wonders. Okay, so for some reason, which I don't really understand very well, these Gaussian processes work extremely well if you only have few points. Okay, so not of course 3, but if the number of points, unlike neural nets where you need a huge training sample, here the number of points is sort of relatively small and you get a very good approximation. Okay, so to very briefly explain Gaussian process, but really very briefly. So I'm not so good in probability theory. So I like the derivation easier if you look at function approximation. So if you want to approximate a function, interpolate a function in more than one dimension. In one dimension, it's very easy to do it, right? You just draw through the function. You can do it piecewise linear or splines or Chebyshev polynomials. But if you want to do it in high dimensions, you cannot do it very easily. Okay, so if I give you 10 points in this room and tell you to find a polynomial that interpolates these 10 points, you'll tell me, well, Mr. Kubler, you have not heard of Haar theorem. It's impossible, and it's impossible actually. Okay, so generally you cannot do it. It's impossible. Okay, so but you can do what's called radial basis functions. Okay, and it's a very simple idea. So a kernel is just some function from a times a to r, which is symmetric and has this property that the matrix is positive definite for every subset of distinct points in A. So this second property is a crucial property. So you might argue, are there even functions? Can you find kernels that satisfy this? And the answer is yes. And the very simplest one that satisfies it is the square exponential kernel. So you can derive for yourselves that if you take this function and get distinct points in any space, so let's take 10 points in this room, take 10 points in this room, form this matrix, this kernel matrix, it's going to be positive definite with this function. Okay. With polynomials, it's not going to be positive definite. It has to be some tricky function. With this function, it's going to be positive definite. But what does that mean? It means clearly that you can use it to interpolate, right? So it means interpolation conditions have a unique solution because K is invertible. Positive definite means invertible. So K is invertible, so you can find a function that interpolates it. Okay. So any points you give me, I can interpolate them as radial basis functions. Sounds fantastic. It's not as fantastic as it sounds because this is typically so saying it's non-singular doesn't mean it's very well conditioned. Okay, so this is typically a shitty thing, so you don't really want to do this. But it turns out that these kernels thrive in a completely different area, which is these Gaussian processes, which is now called machine learning for some reason. So I don't know whether machine learns there, but so there's this book by Rasmussen and Williams, which is a big book and it's a standard reference to look at it. And then there's this famous paper by Scheidegger and Billionis, which brings it into economics. So if you read the book or the paper or my slides, you're going to think it's completely crazy what the guy says. So the Gaussian process is a collection of random variables, any finite number of which have joined the Gaussian distribution. It's so complicated, but it's not that complicated actually. But because it's Gauss, it means that you can specify it by a mean function. So you index the collection of random variables with some x, the real line, and then you have the mean function and the covariance function. So Gaussian process just is a mean function and a covariance function. This covariance function has to be a kernel, so it has to be the kernel matrix has to be positive definite and symmetric. Okay, so for example, it can be square exponential. Okay, so our Gaussian processes, we think of them as being a mean function, which the prior mean, you can do OLS and set the prior mean if you want to approximate a function, that's a prior mean to some linear function, or you can just set it to 0. And the kernel function, which gives you some of this thing that's in the way, but which gives you the covariance. And then we say f of x is a Gaussian process. And as I said, the kernel function The easiest is the square exponential kernel, but there are many others. So there are kernel cookbooks. You can look up different kernels, and it's a little bit like neural nets. All of these things you can spend weeks and months of playing around with different variations. Okay, so the amount of time I replaced square exponential kernel by Matern, this guy is called Matern 2.3 kernels, and by Matern 2.5 kernel, it's just a complete waste of time because the result was always the same. It never worked because I had to bug somewhere else, but I spent a lot of time trying to blaming it on the square exponential kernel. So anyway, so there are a bunch of kernels you can use. Let's stay with the square exponential one. And then you can use Bayesian updating. So you can say, okay, so suppose you have your observations, there's this function f which you want to approximate, but you observe there's some noise. Okay, so here now comes in something which is sort of new, which is noise, and for the theory to work, it's all Gaussian, and the noise is to be normally distributed with some standard deviation s, but the noise can be measurement error, the noise can just be smoothing, so with some noise, and then you can see that the joint distribution of y and f of x is just normal with mean 0, if you take the prior mean to be 0, and with this variance covariance matrix, and you can do Bayes' rule to figure out that the distribution of f of x, which you want to have, is normal with mean m tilde and variance sigma squared tilde. And m tilde is just the kernel matrix of your observations plus this regularizing term s squared I inverse y, so just OLS and then k of x and x. Okay, so this is going to be our function approximation. Okay, so this is our Gaussian process regression. There's this bunch of points. We put them in a kernel matrix, we compute this stuff, and then we have our function m tilde. And we have one more thing. So that's the advantage now of all this probability theory, blah, blah. We have the variance of our Gaussian process. What does it mean that we have the variance of our Gaussian process? Well, formally it means, we have the variance of our Gaussian process, but practically it means we can use it to sort of approximate the quality, sort of assess the quality of our approximation. If that variance is large, we need to add another bunch of points there. If that variance is small, the approximation is probably pretty good. So we can use this to do some active learning. If we build our surrogate model, we do Gaussian process regression. We have our Gaussian process. We can see where it has high variance. There we might have to add some additional points to get the variance down and get the quality of the approximation. Okay. So that's how it works. And then now we have, now we have a black box. You give me any value of the parameter, and I give you the value of the function. And now we can just integrate with, in 1 second, we can just integrate with whatever method we want to. So we can now compute this whole, and yeah, go ahead.
So I just think I'm slightly lost. Like with the f function, initially was the arbitrary object that we wanted to approximate.
Yes.
And now sort of we assume that it has the shape of a Gaussian function.
No. The shape, no. The shape is hidden in this. This is a square exponential kernel. So if you take s to be equal to 0, this is precisely, it interpolates precisely as a radial basis function. So radial basis function interpolation is a special case. So if you take s equal to 0, you interpolate your endpoints precisely with some radial basis functions, with some weighted sum of radial basis functions. Now, you can take the square exponential radial basis function, but it doesn't look Gaussian at all. It looks like a normal approximation because this is a very condensed way to actually write, write this. So this kernel and these parameters alpha are from the OLS regression. So you just write it as a weighted sum of the case. So the Gaussian process thing is just to derive this through Bayesian updating and Bayes' rule. And then at the end, the main practical advantage of doing that, so there are two reasons of doing it. One advantage is you get out the standard deviation, which tells you a little bit of the quality of your approximation. The other one is, if you observed, here I didn't put any L's, and here are a bunch of LIs. So you can put in hyperparameters. You can put in additional parameters into your square exponential, into your kernel, which you can then estimate the maximum likelihood. So if you have all these Gaussian assumptions you carry around, you can do maximum likelihood and estimate these L's and estimate the S and get the approximation extremely nicely. Okay, so now, and then you can just, solve these integrals. So of course you want to have some measure of error. So one error people report is a leave out error. So you take n points and leave 1 point out and see how close your Gaussian process is to the Gaussian process you get without this 1 point. And you take the average of this, and that better be small. Now, of course, if your true model is incredibly nonlinear, or even have multiplicity or jumps or stuff like that, none of these methods are going to help you very much, right? So there's this implicit assumption of enough smoothness in there that if you pick 10 points, you recover the function, or if you pick 100 points, you can recover the function. Of course, if you have multiplicity and you have some manifold, this is not going to work very well. Okay, so and numerical integration, you can use whatever you want to. So we have, Simon has these worksheets here, quite impressive. So if you go to the rep, he has these Python things he uses for teaching. And you can just do 1D, do 2D. So, this is 1D Gaussian process, multi-dimensional Gaussian process. And an interesting one, which I want to spend a second on here, if it works, is this idea of Bayesian active learning, which I try to explain to you, which is to say, you take a few points, and then you look at the posterior variance of your Gaussian process, and where that is big, you add additional points. Okay, so he did the sklearn, Gaussian process regressor, and compute the moments, compute the utility, meaning where you have to add points. And then he has a bunch of test functions, sine, relu, absolute value of sine and clip. And then he plots it. And so if you go down, I'm not going to go through the code because I want to talk a little bit about global warming. It's fucking warm in here. Talk about global warming, man. Okay, so here are some pictures. Okay, so here's your true function, the red dotted one, and you would take 1 point, you put a Gaussian process to this 1 point, and that looks like, you're right, that looks Gaussian, right? Because it's a Gaussian, it's a weighted sum of one Gaussian term. So that looks very Gaussian. And you can see that it has nothing to do with the true function. But now you can ask yourself, what's the posterior variance? And of course, the posterior variance is very large. And where the posterior variance is the largest, you put in another point here. Okay, you do the whole thing. And now with 2 points, it doesn't look Gaussian anymore, surprisingly already. And it's still a horrible approximation, the blue one to the red one, but you see that the variance is also very big. So you put in another point here. Well, the approximation is still not so super good, but you can see that the variance there is very big. You put in a point there. Now the approximation is not horrible. Well, here it's still pretty off, but otherwise it's pretty good. But where would you put in the next point? Well, you would put in the next point here because here the variance is large. So you put in the point there, and now the approximation looks okay. And then, he wanted to show f and put points and points and points. But you see, for example, here, it takes a long time for this to pick up this wiggle here. Okay, so the approximation everywhere is almost perfect, but here it's still very large. But now he puts in the point there, and it gets better. And yeah, so you can play with it. And it's in the GitHub. And I should say it's obviously Simon's thing. I did nothing for it. And now it turns out I stupidly closed my slides. That was incredibly dumb. Where's the In the folder, you think it's?
Yeah, it's showing.
Ah, thank you. Saving me. Okay. Okay, now I do Control L. No. How do you full screen?
The right corner knows the two arrows going diagonal.
The right.
Right top corner.
Send a little recording of the room.
Sorry. Okay, so let me give you an application, global warming, because I think it fits very well and we don't know anything. So we know that it's warming and it's us. Average temperature clearly went up and it's clearly caused by CO2 emissions. And it's warming in Switzerland too. So this is the average temperature in the summer in Switzerland, Basel, Bern, Geneva, and Zurich. And you see that from 64 to 1990 to now, it shifted a lot. Okay, and if you go out, you sort of also feel it. But that has nothing to do with it. So note that 1947 was already a very hot year, nothing to do with global warming. And in fact, this time of the year, 1947, temperature was 45 degrees. So we're sort of lucky that we're not 1947, but only in 2023. Anyway, so it's warming. So what do economists have to say about this, except that it's warming? I call it the Nordhaus program, but it's unfair because there were other people who did it too. But Nordhaus won the Nobel Prize for it. So he said, look, we're a bunch of economists. We know about benefits and costs. So we're writing down a social planners problem. And the guy understands that CO2 heats up the future, and that's bad. There's some damages that come from too much heat. And we can emit less CO2 today, but it's going to be costly. So, you have to build a bunch of stuff or you just produce less. So it's going to be costly. And so what's the optimal amount of money you should spend on reducing emissions? So nowadays it's called what's the optimal price of carbon, but probably not, because the Biden administration decided to price carbon by just subsidizing everything, all clean energy. So the price of carbon stays unchanged, but everything else becomes cheaper. Okay, so if you think about that, Nordhaus had a great idea, but there's all this stuff we don't know. We have no idea about. So future emissions we should know, because that's what economists should figure out together maybe with engineers. But certainly about climate, we know very little. So we go talk to climate scientists, and climate scientists say they know very little. And depending on the climate scientists, they say they know almost nothing, except that it's warming, but by how much? So you don't get a good answer from them. So, and then damages. So why is it bad that it's hot? That's always a question which people ask who sit in the air-conditioned offices on Wall Street, looking down, and they don't give a shit if it's warm or not. Of course, if you work on a construction site in Pakistan, you might have a slightly different view on this, but it's still incredibly difficult to quantify the amount of damages. And you can go out and to the field in Indonesia and ask people how much they suffer from the heat and do a little regression. But nobody's going to know what happens if warming is 2 degrees or 3 degrees and how high damages are going to be. So Nordhaus, he pulled it all out of his butt. So he made up some numbers, literally made up some numbers. And then he made up great stories why these numbers are relevant. But what would be a little more scientific? Well, I don't know, so I don't have a good answer for that, but we can do a little of uncertainty quantification. And let's focus on climate here, okay? So let's focus on climate because it's fun to talk to these climate guys. And I think it brings it a little closer to science. Damages, I don't know what to say. And emissions, we should know, but we're not so good at it. Okay, so there's this. So when we think in macro or finance or uncertainty, we think about exogenous shocks which come every period and are Markov and blah. But the real uncertainty is model uncertainty. So we just don't know. It might not, the whole thing might be deterministic, but we don't know what's going to end up at. Okay, we don't know what warming is going to be. And so obviously scientists spend a lot of effort in trying to figure that out. So there are these gold standard of climate models, which are extremely large models, system models or atmospheric ocean global climate models, which are gigantic. They run on gigantic supercomputers, they, you know, use so much energy, hopefully not generated by coal, but they use so much energy that, you know, an average Pakistani village could live on that energy for 10 years. And they simulate through, okay? So these are large scale simulations. They simulate through, these are super smart people. If you talk to them, they, you know, they can code. They, you know, if they would see this, they would laugh at us so crazily that we do this bullshit hippie stuff, okay? So these are just superstars in this. But, you know, then they make some predictions and they don't agree, okay? So the question is, how can we sort of use what they do and then without the energy supply of an entire country, come up with models where we use the results. And what we use is called climate emulator. So we write reduced form models which sort of match certain things they forecast. So I call it in CMIP we trust. So these research groups, they come together in the coupled model intercomparison project where they all submit, so they get certain homeworks to simulate what would happen if CO2 in the atmosphere would double, what would happen to temperature over the next N years. And they do all do their homework, they come together and they present their homework and then they look at how they differ. And we take that as the true description of the uncertainty here. Okay, it's actually controversial. So if you talk to a lot of climate scientists, they think it's complete bullshit, okay? So they tell you there is non-linearities that, you know, which they miss, and it's going to be maybe much worse or much better, and then or nothing. But you got to believe in something. So I don't believe in God, but I believe in CMIP. So here's what CMIP predicts. So they take scenarios. So these are emission scenarios. The red one is very bad, and the green one is sort of close to Paris. But within a scenario, different groups, so different computer programs, different research groups, produce different predictions. So if you look at the blue one here, the temperature forecast until 2100 differs by, you know, 1.5 degree almost. Okay, so it's maybe these guys are right, and blue emissions are only going to lead to 2.5 warming, or these guys are right, and blue emissions are going to lead to 4 degrees warming. Okay, that's some kind of uncertainty, which, you know, we don't know how to handle. And then in these pictures, you always see the solid lines, but the solid lines are not the expected value, okay? These people don't like to talk about expected values. The solid lines are just the median, okay? You just go through all these predictions. So there are, like, I don't know, 30 groups that put in predictions, and then the median prediction gets a solid line. But it has nothing to do that we think that there's no, you know, no idea that this is very likely and this is very unlikely. This might be, for many people, more likely than this. We just don't know. Okay, so then we take what's called the Nordhaus climate emulator. So it's a very simple linear model of this thing, which is supposed to match what the big models give us. And so, you know, it's just a linear difference equation, which you can simulate through. Okay, but it's a bunch of state variables. So I'm going to tell you then how we solve it. Simon already said we solve it with neural nets because it's a bunch of state variables. So there are 3 state variables for carbon, how much carbon is in the atmosphere, in the upper ocean and the lower ocean. We have a 2-layer energy balance model, so there are another 2 state variables. And then there's some forcing, which comes from CO2 in the atmosphere. There are some emissions, which we need to specify somehow. And then off we go. And then we can see, so in a paper with Follini and Alex and Simon, we can see that we can match CMIP. So CMIP does these experiments, and these are like the CMIP things, and we can match them with the climate emulator. We're just picking different parameters. Okay, so we can match the carbon cycle, and we can match temperature. And so the parameters to match these are actually different, all of them. But to do uncertainty quantification, there's always some correlation between them, which is sort of complicated. So we're going to focus on the ECS here. Okay, so ECS stands for equilibrium climate sensitivity, which is in this model a very mundane object, which is just to say what is the long run steady state of this finite difference equation, when does temperature stay constant if CO2 doubles off in the atmosphere? And there's some number. Now, if you talk to climate guys, they don't see it like that, okay? So the truth is a complicated nonlinear model. So it could be that it stays at some level and then the fly dies and it jumps up another 50 degrees. So the ECS is not something they like to think about, but in our model, it can, in principle, in the long run, be measured from data, but only in the long run. Okay, so, and here are the different values, okay? So this is a range which comes out of CMIP for this parameter. Okay, so then we want to do the Nordhaus program, and we do it a little bit more fancily. So Nordhaus obviously didn't have Epstein-Zinn utility. We have Epstein-Zinn utility because, you know, we are tough guys. We can compute tough stuff, unlike Nordhaus, who, well, now I have to say I'm a little mean to Nordhaus because he was actually, you know, he started this in the 70s. Okay, so the guy was actually a pioneer in this thing, an incredibly good guy to start this on his own. And you know, I was at Yale, and everybody thought that Nordhaus was doing nothing. Okay, so everybody was convinced he had retired because he wouldn't go to any seminars, he wouldn't show up to anything because he was on his own doing this climate stuff, working towards a Nobel Prize, as it turns out. So it's actually, you know, I still remember that some people I know from grad school, when Nordhaus won the Nobel Prize, I couldn't believe it. They called me up, said, "Did you see this? This must be a mistake." So anyway, so Nordhaus had Fullerman Morgenstern, we do Epstein-Zinn. Also because, you know, we want to take a stand on IAS versus. And then what do? So we maximize a planner's lifetime infinite lifetime utility, subject to some accumulation constraint. There's a Kopf-Douglas production function, and there are these damages. Okay, so higher temperature damages stuff. And so in the paper, it's a bit more sophisticated, but for what I want to show here, we just do it with quadratic damages. Okay, so this pi2 is an unknown parameter. We know nothing about it, maybe, but Nordhaus picked some very low value, which everybody hates us for now. But, and obviously, assuming it's quadratic, which is also a very strong assumption, it seems. So if you go out now, it doesn't seem to be quadratic. Okay, it seems like it should be powered to the 10. And so that is one constraint, and then we have the entire climate model. Okay, so then we have as constraints. So the planner obviously in range expectations understands this and this. Okay, so there are a whole bunch of state variables. These climate state variables, capital emissions, and so on. And okay, what is this here? Okay, and then we solve it, and we do what I explained. We actually solve it in neural net. So building a surrogate is very cheap because we solve, you know, we include the parameters as state variables, and we can compute the Sobol indices. And we see that overall uncertainty is very large. So the coefficient of variation is 0.48. That's, you know, so suppose we get out at an optimal carbon price is $100. Within 1 standard deviation, it could be 150 or it could be 50. So that's pretty bad. That's what the world tells you. That's typical economists. On one hand, it could be 50. On the other hand, it could be 150, or it could be 100. So we don't know. And so we're asking ourselves, who is to blame for this? And we do Sobol indices on a bunch of parameters, risk aversion, IES. Rho is the time discount rate. So this is the famous stories, you know. Nordhaus picked this to be very, you know, he picked it to match the returns to capital. And then this English guy, Stern, came out and squashed Nordhaus and said, oh, it has to be much higher. This is unreasonable and typical American, blah, blah, blah. And no, and it's true, it drives part of the uncertainty. But the real killer are the damage function parameter and the equilibrium climate sensitivity. Okay, and you could say, so this is partly driven, so I didn't show you how we did it because I'm running out of time, but you could say this is partly driven by the range you take. Okay, maybe we can pin down this damage function parameter a little bit more by running more regressions on how damages look like so far and this. But this is the CMIP range, okay? So this is a CMIP 5 range for this parameter. This is what climate scientists tell you it could be. And you see that it drives a very, very large part of the uncertainty here. Okay. So what do we learn from this? Except that, you know, Alexandra is a hero in computing these models with neural nets, and we can compute them for thousands of parameters and can do all this stuff. Well, you can learn from this that maybe the way we wrote down the model was bullshit, because if this is really so much uncertainty, maybe the planner should take that into account, right? So we write down this planner's problem for a given value of this parameter, but this parameter is uncertain. And what kind of planner would not take into account that there's uncertainty? Okay, so now, of course, if we embark in this, we have to make a bunch of other very strong assumptions. Okay, so when I started this thing by saying, I also want to sort of try to see if uncertainty quantification is at all useful in economics. I'm still not so sure, right? Because so in engineering, it's clear you can change the model only so much, and you can invest so much money to get a better estimate of your parameters. In economics, you say, okay, there's all this uncertainty, there's this parameter, but we don't know. We can talk to the climate people. We don't know anything about this parameter. So let's change the model. Now, of course, by changing the model, we make 100 different new assumptions, and maybe you don't like them. Maybe you do. So let me tell you how we change the model, okay? So we want to make this equilibrium climate sensitivity uncertain, and we want to think of the planner as learning about it. Okay, so it's actually not us, it was some people 10 years ago, Kelly and Wang and these guys. And they had this idea to have the planner learn about this parameter. But of course, if you want to do learning in any reasonable way, you want to do it normally, so you have to play around a little with it, okay? And so fortunately for us economists, there were these guys, Rowe and Baker, who wrote this crazy paper where they claimed that the equilibrium climate sensitivity can be expressed as some lambda 0, which you get out of physics, 1.2, divided by 1 minus f. Okay, so it's fine. Obviously, you can always do that. And they get it out of a first order Taylor expansion. Okay, you can do that. First order Taylor expansion is okay. But then they say, f is normally distributed. Now you sort of get a little nervous. Okay, so 1 minus f is normally distributed. That doesn't look so good. And then they say, f has mean 0.65 and standard deviation 0.13. So you look at the same 3 standard deviation. So that doesn't look so good. And you know, and in climate science, these people are you know, so there's this guy Michael Gill, who's a close friend of Simon's. He couldn't come today, but he has a house close by. And you know, he wrote these extremely nasty papers saying that these guys were so dumb, and then they responded, and you know, anyway, so I think the consensus now, I actually asked Gil about it, and the only thing he told me was that Celia Peen, his co-author, passed away. Otherwise, he was not willing to tell me more. But anyway, so it's a linear approximation. So clearly, it's locally not bad. So if you take f between 0.65 and 0.8, you're going to do okay. So that's what we do. So we just truncate it at 0.85. Okay. That gives you an ECS of 8, which is outside of our CMIP 5 bound. So ECS of, so anyway, this would give, you know, if you don't truncate it, it makes no sense. But even if you think it gets close to 1, it goes to crazy numbers. Okay, so in fact, I remember I was in this talk, some guy from Chicago gives this talk and he uses this, and he says, oh, somehow I get infinite price of carbon because he's, and then you ask, so by how much did it warm? Oh, it warmed to 30 degrees. So anyway, so we're aware of all this, but we still do it, and then we just truncate the normal distribution at 0.85. And then, you know, you can, Bayesian learning and truncated normal is very simple. So we rewrite this, temperatures observed every period. People don't know whether it comes from some temperature shock, just a hot year. or it comes from a high F, and so they use Bayesian updating to update this, and they learn. Okay, so now we endogenize the uncertainty about the ECS into the model. And we can again ask, how does UQ look like? And now, so the first graph I showed you is over a year old. At that point, we didn't know about Shapley value. Now we're actually also reporting the Shapley value in blue. So that's a main thing here. So this is the Shapley value, it's very important. And now the largest uncertainty comes from the damage function, which is sort of clear and, you know, sort of obvious. The prior mean, there's some uncertainty, but you would think that the prior mean is not something you should play around with, because the prior mean in principle, you can claim that this is just the average of what the single pi people produce. And so 0.65 is the right value. So this uncertainty, we might be able to take away. The standard deviation adds very little. Rho still adds, you know, quite a bit. And now, let's not talk about this, okay? And then you could argue, so lastly, you could argue, okay, there's still a lot of uncertainty here, but all that matters for this, for the prior mean, is subjective beliefs. Okay, we could just go out and ask the planner or ask people, what should the planner do? What is the belief about climate change? Now, if you do that, you unfortunately find out that it's very heterogeneous across people, okay? So among Americans, and very, very, very persistent. So in the last 10 years, Americans changed their belief about climate change, almost nothing, okay? And it's very heterogeneous. So these are the guys who are alarmed. They probably think ECS is pretty high, became a little larger, but these guys stayed absolutely constant. And so, you know, more of what is the right mu to use. It's not a scientific, I mean, it's a scientific question, but it's not a climate science question anymore, but it's a question of what should the planner do? Should the planner be optimistic, like 50% of Americans, or pessimistic, like the other 50%, or something in between? Anyway, so that was just an illustration of the stuff. So the main thing is you can compute these Sobol and Shapley indices relatively efficiently if you have a good surrogate model. And a good surrogate model can be with neural nets, so in fact, in the paper, we have a combination. So we have the neural nets, and we compute for all parameter values, we solve it for all parameter values, but then we also have some quantities of interest which we only get out of simulation. So we have to simulate the solution to get these moments. And so then we build the Gaussian process surrogate value on top of it to get to our integration. Okay.
So you mentioned in the beginning we use neural nets for sort of estimate the parameters. I think you talk about the dynamic programming part is still solving the model, or you already talked about it. So which moments you want to match?
No, so we're not matching any moments. So we solved the dynamic programming problem, and the parameter. So now you are putting, you know, you're saying in a nice way, but I'm paranoid. I think you're trying to go after me, which is fine. So you're absolutely right that you might take the standpoint that the economic parameters rho, psi, and phi, or gamma, should be pinned down by data. And we should estimate them from data. We don't do that. We take them to be uncertain and do uncertainty quantification over them. But on the other hand, it's a planner's problem, right? So if it were a model of the economy, if you would say, oh, it's a representative agents model of the economy, then you're right. Then we want to write down a model which matches historical data in terms of parameters. But the planners, you know, this whole debate between Nordhaus and Stern is sort of, Stern didn't doubt that you need a row of whatever to match the return to capital, but he doubted that it's a morally just row to put in the planner's problem. So that's why I think it's sort of, you know, sort of okay that we don't estimate them, but we take them to be, we are agnostic about them, and we just do it for a range of parameters and quantify the uncertainty about it. Having said that, the uncertainty that comes out of that is pretty small, right? So here, in this formulation, the preference parameter, except for the row, none of the preference parameters does anything for the variance.
I didn't see how deep learning is really.
Oh, we use deep
outside the
learning.
quantification. However, it's still like using.
To solve this.
Logic process.
No, we solve this with deep learning,
Yeah, I know.
this dynamic programming problem,
Solve this.
for all parameters. So we include the psi, the phi, the pi as state variables in the dynamic programming problem. And it's high dimensional enough to use deep learning. That's all.
So with many times.
No, once, the old parameters, conversions and exhaustions state variables, and then you have a huge solution surface. And then what you look at, for instance, is the social cost of carbon.
Okay, so I'm done. You can.
No. Yeah, that's what my understanding is. You say you are using deep learning to. It's solving many times, but it's not matching objective. So
Yeah, then what is
it's close to the right stuff.
Okay, if there are any other questions, you can come and ask me afterwards or